Uh, I'm actually happy to introduce Jaewon Kim today, for who's the speaker. Jaewon's currently a postdoctoral associate in the Laboratory for Information and Decision Systems at MIT in Boston. Before joining MIT, he received his PhD from Texas A&M University this fall with under the advisor Dr. P.R. Kumar. His research focus includes cyber physical systems, cyber security for cyber physical systems, system identification, machine learning, multi-agent unmanned vehicles, uh, middleware, real-time resilient networks, and cloud and fog robotics. And on a personal note, Jaewon was one of my mentors during my master's at Texas A&M, where he helped me research with a lot of robots and mobile robots and ground vehicles. So yeah, I'm really happy to have Jaewon present about his research.
Today, I'm going to talk about cybersecurity of network cyber physical systems. First, I will talk about the theory of the cyber attack defense methodology called dynamic watermarking, and then I will show some applications of dynamic watermarking. So let me introduce me first. I am Jaewon Kim. I finished a Ph.D. from Texas A&M University, Electrical and Computer Engineering Department, August 2023, and I started postdoc at MIT from September 1st. Okay, so what are cyber physical systems? Cyber physical systems is called CPS. It's next generation of engineered system in which computing, communication, and control technologies are tightly integrated. So what does that mean? Traditionally, the internet was, I can send message to you, you can send message to me, and also I can check your web page, you can see my web page. Those things are all transaction of bits. But in CPS, these bits affect real world. So you make things happen in CPS. So I can also say these are network control systems where multiple network computing nodes and diverse heterogeneous intelligent agents interact with physical world in real time. So let me give you an illustration for better understanding. So CPS is tight interconnection of physical system such as plants, processes, systems, and cyber components performing a computation connected by network, potentially network. So this is the picture of my lab when I was in PhD. I have some ground vehicle as an aerial vehicle. Yeah, there is a physical layer and a cyber layer. So here are some examples of cyber physical systems. For example, autonomous vehicles, chemical process control systems, and unmanned aerial vehicles, and even the solar PV power systems. There are many systems are cyber physical systems. Okay, so security of cyber physical systems. Why it is important? Many societally critical systems are being networked, such as smart grid, autonomous vehicles, and unmanned air vehicle transportation, process control systems. They are safety and economy critical. So malfunctioning causes considerable physical and economic damages. So that's why security of cyber physical system is very important. Actually, there have been many attacks in the real world. The prominent one was Stuxnet, 2010, and Ukraine Power Grid, 2015, Ohio Nuclear Plant, 2003, and Shaman malware, 2012. So how can we possibly secure cyber physical systems? So here are many recently reported cyber attacks in real world. So such as Stuxnet and Black Energy. The Black Energy is actually the power, cyber-induced power outage in Ukraine power grid. The attacker used malware called Black Energy. They are actually compromised the three power utility companies and leading to power disruption in the region for half of the population. And most recently, the Colonial Pipeline cyber attack, which is ransomware infection, pays $5 million and increases gasoline prices, something like that. So that's why cybersecurity is very important. Okay, so abstraction of network cyber physical system. So overall system has physical system and actuators and some sensors and some routers and computational nodes, information fusion node, and they are connected over the network. However, some of the nodes may be malicious, may be compromised. So how do we secure the overall cyber physical systems? So these network CPS are vulnerable to potential arbitrary cyber attacks where malicious agents compromise the sensors or the networks carrying the sensor measurement. So some of the sensor could be malicious, could be compromised. We say the sensor is compromised if information from a sensor is compromised. So how do we secure this CPS? So let me give you an example with a cyber physical system with malicious sensor. So during the normal operations, the sensor measurement is exactly equal to the reported measurement. Here, the ZT is reported measurement from the sensor, and YT is actual measurement from the actual value from the system. So if the sensor is honest, those two values should be equal. But some sensors could be malicious, and they are reporting the first measurement can cause critical damage to the system, like Stuxnet. So what is the solution to protect overall cyber physical system? There are actually many solutions, but I'm going to talk about my solutions, which is dynamic watermarking. So I'm going to talk about cyber secure operation through dynamic watermarking methodology. So here is the dynamic watermarking method for detecting potential attacks. So during the normal operations, the sensor is keep reporting the sensor measurement. And then there is a control input U. U is depending on this GT. So that's why if the sensor is malicious, they can break the system. So to protect these cyber physical systems, we are injecting a private random excitation signal ET, which is watermark. It is superimposed on the control input UT. And why is it called watermark? Because it is indelible, like a watermark on a sheet of paper. It cannot be removed from the sensor measurement. And then new control input U plus E, UT plus ET is going through all the way the system and come back to the attack detector at the actuator side, can check if reported measurements are appropriately correlate with the random private excitation ET. Then we can detect attack. So let me give you an example with the single input, single output equation. Here is the system equation with the system noise. So xt plus 1 equal to ax plus bu plus some noise. And then we are injecting watermark onto the control input ut. So new control input ut will be ut plus et. Then the closed loop equation we can write like this. And then we can reorganize this equation two different ways. The first equation is watermark on the left side, and second equation watermark on the right side. So we will use first equation for test 1 and second equation for test 2. So like this. So in the absence of the attack, those test 2, the first equation should be equal to the system noise variance, and second equation should be equal to system noise variance plus some watermark variance. So if either test fails, then there is a malicious sensor information in the system. So after detect attack, system should goes into the safety mode, hearted, rebooted, manual operation, etc., etc. And there are trade-off for setting detection threshold. So if we set high threshold, will result in more miss alarms, and if we set the low threshold, result in more false alarms. So we have to carefully choose the threshold setting. Okay, and then this dynamic watermarking methodology has been experimentally tested on process control systems, mechanical system, in this case, a helicopter system, and vehicular system, autonomous car, and also the power system with power electronics, which is grid-tied inverter system. The benefit of the dynamic watermarking methodology is general purpose proactive methodology for defending control systems against any cyber attacks. Okay, so from now, I'm going to show the experimental test demonstration. First will be, oh, give me a second. I will talk about why do we need experimental testing first? Because experimental testing is very important for this dynamic watermarking method. So why do we need experimental testing? Because dynamic watermarking is fundamentally based on stochastic considerations. Here is the picture from the process control system testbed. So the froth in the water flow into the bottom tank, which constitute noise, is quite substantial. So you can see in this picture. And there is no mathematical model for this froth noise. So, and also critical issue is, does the tiny watermark signal that is superimposed survive passage through the froth? Also, how small can watermark be? Therefore, one need to test by experimentation, not by simulation. And also there are other reasons why we need to do experiment. First, the dynamic watermarking method calls for actively injecting noise into the control system. We have to check does this affect normal operation? And also the lower variance of the signal employed, the longer potentially is the time to detect an attack. So what is the trade-off between miss alarms and false alarm? And what is the detection delay? And the dynamic watermarking is designed to be a general purpose methodology for defending against cyber attacks, any attacks on control system. So we have to check it. Is it general purpose? So therefore, defense methodology against cyber attacks that fundamentally relies on stochastic consideration needs experimental validation, not validation by simulation. So that's why experimental validation is very, very important. Okay, so first example I'm going to show is the process control system. So the experimental testbed is a coupled water tank system. So there are two tanks are coupled, and there is a water pump here. And water pump feeds into the tank 1, and which in turn feeds into tank 2. So input water flow is going to tank 1, and tank 1 will feed tank 2. So this testbed controller is designed to regulate or track the water level in tank 2. So how can we measure the water level? The water level in each tank is measured using a pressure sensitive sensor located at the bottom of the tank. This is a prototypical process control system. And then I check the watermark effect on the normal operation. So the first column is pump voltage, which is control input. And second column is water level, which is the measurement. And we injected the small watermark with the different variants, and we try to minimize the injection, the watermark level. And then second picture here in the middle. So it's overlapped all of the no watermark, watermark variance 1, and watermark variance 2. So we concluded that the dynamic watermarking does not cause any significant performance degradation. And then here is the video. I'm going to show the video. So we are right now initiating the blend. And the set point is 15 centimeter at the bottom tank. In the absence of the attack, the water level is controlled properly. And then attack happened here, but the system doesn't know without any defense methodology. And then there's a dynamic watermarking test 1 and test 2 are real-time running here. And once attack is detected, and stop all of the plant and drain all of the water for safety. Okay, second example, we tested on the two-rotor aerial vehicle flight control system, so which is consisting with the two rotors, front rotor and back rotor, which is exactly similar architecture with the Boeing HC-1B Chinook helicopter. They have a 3 degree of freedom, so pitch axis, elevation axis, and yaw axis. And we attack on the elevation measurement. So before we attack, we tested on with the manual operation, with the manual control input. So we connected to the joystick to test the manual control input to the plant. Then we can understand how much input is needed for the helicopter. Something like this, then forward, then backward, then takeoff and landing. Yeah. And then after that, we set the trajectory for helicopter mission, and then attack and defense. So here is the autonomous trajectory for helicopter, and we keep monitoring the elevation measurement. So in the absence of the test, helicopter is running properly. And malicious sensor is working correct system instability like this. All because of malicious sensor information. And then now dynamic watermarking test 1 and test 2 are running real time. In this case, once attack is detected from the attack detector, we have to switch it to the landing controller for safe landing. We cannot stop the helicopter in the middle of the air. And then after this, we also tested on the autonomous vehicle, which is the Lincoln MKG, which is commercial vehicle, and we changed it into the autonomous vehicle. This one was working with the mechanical engineering department in Texas A&M University, which is called TAMU Autonomous Research Vehicle. It has a drive-by-wire system, and we attack on the yaw rate sensor measure. So the attack scenario is like this. So before 10 seconds, the normal operation, we set the trajectory, which is circling at desired linear and angular velocity. And at the beginning of 10 seconds, we injected a random noise with the variance of 0.5 rad square per second square is superimposed on yaw rate sensor. And after 10 seconds, you will see small oscillation on the steering wheel. Here is the video of the outdoor view and indoor view. So driver is still sitting in the driver's seat. This is the autonomous vehicle. For safety, the driver is sitting on the driver's seat for emergency. So here is the video. So right now, this is normal operation is making a circle. And then you can see here oscillation. And then dynamic watermarking test 1 and test 2 are immediately detected. Okay, so after we test the autonomous vehicles, and this is my ongoing project. So we are trying to secure the energy system. So the test bed is defending against potential attacks on grid-tied solar PV power distribution system. So PV dominant system distribution grid are also CPS. The attacker can compromise the system by manipulating devices at the grid edge. So how to defend PV dominant distribution grid against potential cyber attacks? So that's the motivation. And then we test it in the lab first. We configure the test bed in the lab. we use the two DC source for emulating the PV, and we connected to the inverter 1 and inverter 2 in the same grid. And then here is the attack result. First, we attacked on the inverter 1 with the harmonic distortion. So you can see this pink oscilloscope graph. Here is the attack happened. Before attack is normal operation, and after attack, there is some harmonics distortion. And then dynamic watermarking test 1 and test 2 for inverter 1 and test 1 and test 2 for inverter 2. So as you can see here, dynamic watermarking test 1 and test 2 for inverter 1 is only showing a jump, which is indicating, oh, there is attack, there's something, some malicious events are going on in the inverter 1. And then inverter 2, we attack on the amplitude reduction attack, 100% to 90%. And in this case, only dynamic watermarking test 1 and test 2 at the inverter 2 showing jump. So through this experiment, so we can actually detect the attack. Also, we can identify attack location as well. So which is very important because if there is 100 home is connected to the same grid, so we have to know which home is under attack. So dynamic watermarking can detect attack. Also, we can identify which home is under attack. So that's why dynamic watermarking can use it for anywhere. And then this is ongoing project, huge contract from DOE funded project. The professor, Dr. Kumar and Dr. Enjeti and Dr. Lashe is we are working with them. And actually, after we tested in the lab, we visited we have an industry partner, which is Centerpoint Energy. We visited their actual solar farm. They are providing energy to the grid using the renewable energy source, which is solar farm. I visited and I talked to them as well. And yeah, they have a 3 solar farm. First one is called Oakville Solar Farm. It's 8,000 solar panel, 2.5 megawatt solar inverter, and solar field has 2.7 megawatt. And they have Borkman Solar Farm. Borkman has energy storage as well. So ESS means energy storage. And then Troy Solar Farm, they have 150,000 solar panels, which is providing 50 megawatts. So right now I am testing this dynamic watermarking methodology on the rear solar farm. So which is my current project goal. My current project is at the end of the year. So this is year 3. So we have to test. We have to test in the real world control system, which is solar farm. So maybe in the near future, in few months, I will implement it in the solar farm, and maybe I will let you guys know as well. Then this was when I was at Tamu, I was working on some turtle boat and some cars and drones and jackal, some robotics. Yeah, that's the end of my presentation.
I actually have a question to start off in that case. I did see you talk about the cybersecurity testing with the Lincoln car, right?
Yeah.
For your you did say that in the ideal scenario for dynamic watermarking, when you find an attack, you want to stop the system. So
Yes.
how does it work when it's in a self-driving car? Because you may not want to just stop the system at that sense. You might want to have so I like divide my questions into two parts. One would be like, how did you run it when you had the experiment? Like what happened when you detected the attack? Did it just like disengage, or did it was this carried offline with records from the car? And my second question would be, how do you see this extending to a real world cybersecurity system where just turning off the system or just stopping the system may not be the right safe step to do?
Yes. So you are asking about the mitigation plan after attack, right?
Yes.
So yeah. So dynamic watermarking test one and test two are basically only focusing on attack detection. This methodology is only focusing on detection only. So this methodology is they don't care about the mitigation plan. So mitigation plan is after detection. So post detection behavior should be different based on the system, different according to the system. So for example, for autonomous car, we have to uh, maybe we have to guide them to the roadside or something like that. And for UAV, we have to change to landing controller. And for process control system, we have to stop and drain all of the toxic chemical or something like that. So that work is exactly what I'm working on right now. Because dynamic watermarking cannot tell you what will be the best mitigation plan. Dynamic watermarking is only focusing on detection. But for mitigation plan, detection is the first step. So we have to detect first. Then after detection, so the mitigation plan should be initiated. But the mitigation plan, the trigger, should be connected to the dynamic watermarking test one and test two. So that is exactly what I'm working on right now for mitigation plan after detection.
Right. But how was it when you ran the tests in the lab? Did you take over the control as soon as the attack was triggered, or were you able to like safely stop the tests? Because you have no mitigation system, right, when you run the tests.
Yeah, in the lab, I mostly the stop the control stop the all of the control system and just drain
Take
all of the water and yeah, or
okay,
take the controller or change it to landing controller or something because we
right.
cannot trust the current controller with the malicious sensor information.
Yeah, yeah, that makes sense. Thanks.
I have a question.
Mm-hmm.
Right. You mentioned about detecting uh, the intervention or hacking using the watermarking. So, how do you handle the cases of false alarms, and how do you reconfirm that was actually an attack happening?
Oh yes. So that's why I talk about the trade-off between the setting of the threshold setting. So you basically before I set the threshold, I have to test all of the normal operations level and attack level uh, and the sensor malfunction level as well. Because that's why I was talking about the experimental validation is really important because we don't know the noise, system ambient noise without experimental testing. So simulation is not enough because of the setting of the threshold setting to distinguish between real attack and sensor malfunction or some uh, some sensor problem or something like that. So we can set up the threshold only can reach uh, from the cyber attack. Then only cyber attack happen can reach the threshold and we can say, oh, there is a cyber attack. This is and below the threshold, and maybe we can say, oh, this is sensor malfunction or this is something going on, but not cyber attack. Something.
Okay, and also, does it make sense to do multiple probing to make sure that the attack was a valid one, or is it uh, just dependent on the threshold that we are setting?
Uh, multiple means what? Can you repeat?
Yeah, even after one attack was identified,
Mhm.
do you think it makes sense to check once again or just to reconfirm uh, whether it was a false alarm or not?
No.
Yes.
So once the dynamic watermarking test, any test one or test two, say there is something happened, we have to stop and we have to check it, and we will check it first, and we will initiate,
Okay.
because
Yeah.
without checking, it's very risky, because it's a moving car and moving drone, moving helicopter, and also the chemical process control system is very dangerous. So
Yes.
once we receive the notification from the test one and test two, or from attack detector, we have to check. So we have to be more conservative for safety.
Yeah, I understand. Thank you for your answer, clarification.
Mhm.
Thanks so much for presenting your talk and spending your time to share about your research.